Okay, so I have two statements. The second one is more important, but for that I need you to help me. So everyone, please take out your cell phone. Out. Put it on a camera mode. Okay? Zvi, put it on silence as well. Okay? Put the camera and take a picture, please. Okay? So the first statement is that you are all invited to the summer school that we are organizing together with the Nano Center about self-assembly. We all heard a lot about self-assembly, so now you have a poster on your camera. The second statement is that what you have just done is actually you did physics, okay? By taking these pictures, and I'm going to show you how you can do very complicated physics just by using your camera, okay? And the talk today is about entropy, and it's a very complex subject to some of us that study the thermodynamics. But I want to show you that taking a picture like you did now is actually equivalent of doing a very complicated physical problem. So I will start by acknowledging those in my group that are actually doing all the work and the students. And in particular, I want to mention two students that are responsible for this research, and this is Ram and Micha, in particular Ram, that I think that most of you here know. And they did just an incredible job in general, but also in this work. So my lab, as some of you know, is all about nanobiophysics, the combination between all the sessions here, I guess, the nano and bio and physics, and using chemistry as well in between. And in fact, and this is very, fulfilling, at least for me, to the things that we do. But it's also very expensive, right? I mean, we need to run a lab. The lab is occupied by small angle X-ray scattering, purification method, and all kind of microscopy. And all of that costs a lot of money. And ever since I was a kid, I was programming when I was a kid. I had this vision, right? And many of us also hold this vision today. I mean, we know the Schrödinger equations. We know Newton's laws. We know the molecules that the Itai is synthesizing. Why can't we run it all on computers? Why can't we know the answers to all of our problems, superconductivity, what happens with graphene, what happens with molecules in our body? Why can't we just run simulations and get the answer right? One of the reasons for that is because although that we know all of those equations, and those of you that came from physics knows all of those equations of thermodynamics, know that there is one big problem in computational physics, biology, or whatever it is. We cannot simulate, no matter how good is our computer, all the configurations in our system. There are just too massive amount of states that you need to simulate. And because of that, we cannot get, using a computer, we cannot get a very important quantity that is needed to the understanding of the problem. And this is entropy. How many of you knows what entropy is? That's a majority. Okay, for those of you that don't, Zvi, the thing with the phone is not done. You can leave it. The things about entropy is counting. It's counting how many states are there. Okay? So basically the problem is that we need to count all of them in simulations in order to get this number right. And people developed all kind of computational tools in order to answer these problems, in order to calculate entropy. But this is a very, very difficult task that usually require additional calculations in order to get the number right. And this is a problem. So if we have a supercomputer trying to simulate the protein that Itai made, and now we need another farm of supercomputers to run in parallel in order to get the entropy right. So that is not really practical. So if I'll just cite, really, known people that got the Nobel Prize and so on and so forth about what's the biggest problems in those computations, they all stay to the fact that those are really specific calculations to specific problems, so there's not a general way to do those calculations, and they're usually involved in a massive amount of calculation, as I told you before. And then this guy that some of you or most of you know, my student Ram, came to me one day and told me, Roy, we need to have a talk. I said, what do we need to talk about? I said, I have a project that I was running on my free time. And I told him, Ram, we already know the first problem in your project. You have free time. And then he said, no, I was working on the way to the university. I'm taking the train every morning, so I was working on the train. And so physicists and trains goes, a long way. And I sat down and listened to what he had to say, and I must admit that he shocked me. And this is a good time to tell all of you students, because we have so many students of you, you should, as long as you don't get fired, you should actually do that, right? I mean, you should envision your own project and pursue it without us telling you. This is the key idea of why one would want to pursue a PhD. And Ram did it magnificently. So I'm going to tell you a story about how Ram thought about calculating entropy and what we found out. So the whole story about this entropy thing dates back to these really terrifying looking people. So those are the fathers of information theory. So here on the left is the man known as Shannon. This is Kolmogorov, and this is his student Sinai. And they actually invented the notion of information theory for decoding messages and really laid the foundations for cryptography in computer science. They use this term that is called information entropy. Shannon used this information theory that is resembled exactly to the entropy that we use, the same equation that we use in physics for thermodynamics. The basic concept behind Ram's idea dates back to the fact that this information entropy is actually lays the basic grounds to compression algorithms. And what are compression algorithms? When you want to send a big file and you use zip or rar, I don't know what you're using, this is the foundation that it all dates back to the foundations of this Shannon entropy. Basically, there is a limit how much you can compress a file. And the limit is this Shannon entropy equation. So I'll be a little bit more specific, but beforehand, computer scientists, which are super smart, and mathematicians, which are even smarter, found out that this really does not depend on the details. Meaning that almost any type of compression algorithms, as long as you have a big enough file, the ratio between the file after compression to the file, the original file size, will be this Shannon entropy limit. Okay? And this is magnificent. And again, computer scientists and mathematicians know that forever, like 20 years or 30 years. So, how does those compression algorithms, I mean, we just push a button on our computer, it makes zip, or if we take a picture with our cell phone, it actually already zip it to make it a smaller one, so we won't use 12 megabytes for every pictures that we take, so it shrank down significantly. So the idea, the basic idea behind most of the modern compression algorithms dates to the works of Avraham Lampel and Yaakov Ziv from the Technion. They actually invented an algorithm, a super efficient, super fast, that scans the file. And every time that in the file, in the binary files that is stored in our computer, it finds a pattern that it already saw before, it just makes a pointer. It just said, okay, I already saw that before, so let's just go over there and look at that. And on a large scale, that is compressed more and more to the point that for large enough files, it actually satisfies Shannon entropy limits. It always comes from above. I mean, it's still the compression algorithms made by humans. So these pink things will always appear again and again in the talk. It gives us an upper bound estimate to the entropy. Okay, How good are compression algorithms? Well, they are damn good. And the reason for that is that we use it in everyday life. And actually, compression algorithms are being used in many different places. For example, they are being used to monitor the stock market, to see patterns that are repeating. It's being used to measure variations in blood pressure. It's being used to look into sequences, genomic sequences. This is the one that I like the most. It's being used to monitor our brain waves, compression algorithms, okay? Not, entropy, no physics, right? Compression algorithms to monitor the brain waves to see whether a patient goes into anesthesia or not. Again, these are patterns. We just want to see whether patterns repeat or change. Recently, it's been also used, compression algorithms, to detect phase transition. Moshe talked about phase transition in systems. So it's been used to look into simulations of magnetic systems, liquid crystal systems. And just recently, like a few weeks ago, it was accepted, a paper by friends of us in the Technion, Dov Levin, and in New York, Paul Chaikin. And when they use compression algorithms to study phase transitions in out-of-equilibrium systems. So what is still missing? So we want to do physics to real problems. And for that, we need, as physicists usually do, we need to have the right units. And what people actually use those compression algorithms, all of those examples that I gave you, was actually to detect when things are getting very different. This is what we call phase transition. And what we wanted to do, and we identified it as a problem, is we wanted to do these subscripts. We wanted to take kilobytes of data coming from the compression algorithms and transfer it to K. Boltzmann, the units, the right units for the entropy. And the reason for that if we transfer everything to the right units in physics, we can solve the equation. We can actually understand what is the energetics of the problems, the right energetics of the problem. So let's take a simple case. So the physicists know that as an Ising model. This is the simplest case for physicists in the second year or something like that. For the sake of simplicity, imagine that we have the tiles, like we have the tiles here on the ground, and in each one of them there is a small magnet. So it can be either, north or south, the magnet. And now we want to see if we have interactions between the magnets. We want to see whether they are going to face this way or the other way. So we can run this kind of a simulation on a computer with some kind of a strength interactions between those two magnets, and they will be just represented as, arrows facing up or facing down. Now, if I want to know the entropy of that, I can do a simulation for that. It's relatively easy. But if I want to do the simulation, it'd be represented on the computer like 0 and 1, right? Whether it's up or down, it will be 0 or 1. Now, what is the entropy of this system? I can compress it. I use zip. And I get a smaller file that was represented. Is that the entropy of the method, the entropy of the system? The answer for that is no. And I can prove it to you. I'll take just for the sake of I'll need it later on, I'll take this ratio between the file size after compression divided by the original file size, and I call it kappa. So here it's going to be kappa d. Kappa d is not the entropy of the system. What is the entropy? How can I prove it to you that it's not the entropy of the system? Let's take simple cases that I know the answer for. So if I'll take the degenerated state, the case that all of those magnets facing one direction, right? So I have a big file of zeros, very ingenious file. Okay, now I'm going to compress it. The entropy of this state is 0. But when I'm compressing this file, I don't get a 0 file size. Why? It was designed, these compression algorithms, by humans. I'm going to have headers. I'm going to have all kind of junk there. And the file size is going to be finite. So it doesn't represent me the entropy. I'll give you another example. Let's take the other extreme. When everything is random. When everything is random, and I'm trying to compress 0 and 1, which are placed at random, if I'm going to try to compress the file, I'm going to get a file which is larger than the original one. What I should have got was 1. What you should have got that the file didn't compress. But this is not the case. Why? Compression algorithms was designed by humans. not by physics, right? Okay, so this is a problem. So how can we solve that? We solve that by identifying the this ratio, taking the one that I want to know the answer, this kappa d, the file size after the compression that I want to understand. If I'm taking out the headers, when I compress nothing, and divided by the fully random case, minus the headers, it is guaranteed to be between 0 and 1, no matter what. By definition, this is the maximum entropy, this is the minimal entropy, so I know it's going to be between 0 and 1. And then we took a leap of faith, and we just did the most stupid thing that one could do. We just said, let's try to imagine that the entropy of the problem that I'm interested in is just this ratio, and I'm going to multiply it by the maximum entropy of a system. In this kind of a two-state system, the maximum entropy is log of 2. So I know the answer. And I know what you're thinking. There is no way that this is going to work. Right? I didn't think it's going to work as well. But it does. That's it. That's the whole magic. So now you know how to calculate entropy using zip. And entropy is very complex, right? I mean, when you study that in undergrad school, you knew that this is a very complicated problem. So I'll show you, just demonstrate to you, that this is actually working. That's what I'm going to do in the next 10 minutes or so that I have. So this is the easiest problems that one could do in undergrad studies. You take a 4-level system of energies epsilon, 2, 70, and 80, for example. And over the different temperature, I know how to calculate the entropy. This is just a textbook calculation of the probability to have an energy state, and this is just the straight line that you see over here. Now, but I can run a simulation, and in these simulations, I'll have a particle that will be in one energy or another, and it depends on the temperature that I'm simulating it. So it's a very simple simulation. It's a 10-line code simulation. And then I can take in a certain temperature to have all of those strings of 1, 2, 3, and 4 that are coming in a random way, but not really random, right? And I'm just taking that, and I'm using the compression algorithms, and that's it. And I'm getting the circles here to just fall on top of the line. And in physics, this is what we usually say. In physics, we say that if the simplest problems works, all the rest is just math. All the rest is just complication. This is what we teach on undergrad level, not the compression algorithms, unfortunately, yet. But this is what we teach, how to calculate the basic idea of few-level system, because this one we can compute easily. So the next level is to actually do something more complicated, like these tiles with the spins that are or magnets that are facing up or down, interaction in different temperatures. And in order to do the line here, which is the analytical theory, you need to be Onsager. It's an acronym for a very smart man, a physicist that did a very complicated calculation. But we don't need to be that smart. We can use compression algorithms. We use zip in order to know the answer. And it's super fast. You can run it on your phone. It just takes these images in a certain temperature, many of those, like 5,000 of those, and you get a result which is 1% difference from the analytical answer. And you don't need to be super smart for that. Just use how much the picture can be compressed. And it can be done with so little amount of simulations frames in order to get the answer right. And you can even do like more complicated. We heard yesterday Itai try to explain to you the frustrated triangular lattice. So this is the classical example of those things. So this is a much more complicated things to simulate and to get the entropy right. But we can actually capture that. And the answers are, using these compression algorithms, are so good and so smooth that we can actually differentiate that. This is something usually very hard to do if the signal is very noisy. But here we can differentiate it and get transition temperature and get a specific heat quantities. And again, I'm just comparing here the circles are data coming from compression algorithms on the simulations, and the straight lines are analytical answer to the problems. So then Ram came to me and told me, well, listen, Roy, that was easy. I said, no. But said, yeah, it's easy. Why it's easy? Because it said I want to do something more challenging. If we work with protein, for example, things are not sitting on a lattice. Things are not coming with quantas of energy like that. They are free in space, right? And I want to go and do some modeling, do some simulations on things which are off lattice. Now, this is a big problem, and the problem is that if I'm doing finite sampling, if I'm doing a simulation which is not infinitely long, the least significant digits that I'm going to simulate, right, I'm having, in space, I'm going to be here or here and anything in between, the least significant digits are going to be random because I didn't sample enough. In random, we cannot compress. It just gets inflated, you remember that. So we'll need to do some kind of what we call coarse graining. We need to somehow bin the data to quantas that are good enough for us to use these compression algorithms. And I'm going to show you how. So for first thing that we did is use a model that we know the answer. So we took a polymer, like a string, right? And string, if you hold it in two places, it can fluctuate between all kind of configuration. And as you take the string and push it back, the two ends, the number of configuration goes down, right? If I'm going to hold it all the way, stretch all the way, it's going to be one configuration. It cannot fluctuate anymore. And we know exactly how it's going to die off. It's going to die off, the entropy is going to die off like R squared, like the distance between the two ends to the power of 2. Okay, so we can simulate this kind of fluctuating polymer. It's called an ideal polymer. It's a relatively simple simulation as well. And what we did here, okay, so this is the simulation. And we can actually take the simulation and what we did is that we bin the data to each angle between those two ends according to they can be in 2 pi, so we just, bin it to specific amount of states that they can be in. Specific angles. Between 0 and, 10 degrees is going to be one bin, 10 degrees to 20 degrees is going to be a second bin, and so on and so forth. Okay, that really died off. Now, after we have those number of bins that we have over there, we can use the same algorithms as before. Why? Because now we have certain amount of bins, certain amount of states as before. So I can use my equation as I had before to calculate the entropy. But you're going to say, hey, Roy, you just invented something new. You just added up another parameter, right? You added up the number of bins. But what I'm going to tell you that this amount of bins is actually related to how many frames I calculated. It's related to the level of information that I have in my system. But this is the beauty of it. It's not really a free parameter. Why it's not a free parameter? It's not a free parameter because compression algorithms, as I told you, always give me an upper bound. It's not just anything. It's an upper bound to the real entropy. So if I'm going to calculate the level of entropy that I have in the system, and the number of states, the number of bins that I have there, I'm going to have something very interesting. If I'm increasing the amount of bins, I'm adding more information to the system, the entropy will go down. The entropy evaluations that I have is going to go down. However, because I'm now gaining more and getting closer and closer to the right value. However, there's going to be a sweet spot. There's going to be a minima. Why is that? Because at certain point, I'm going just to add noise to the system, and this cannot be compressed. So the function will go up. What I'm going to use as the entropy value, or this NS that I'm going to use, this number of states, number of bins, the minimum value that I found here. Why? Because compression algorithms gives me an upper bound. Okay, so this is really nice. Does it work? And in fact, it does. So here on the right, you can see the evaluations. How do I find what is the number of beams that I'm going to use. This is here. And on the right, you can see our simulation and the straight line, which are not the fit, but the theoretical values. We can actually normalize all of them by the number of beads that we have on this polymer and get a complete scaling for all of the experiments on the computer that we have done. So this is all nice, but all what I show you up until now were results to things that we knew the answer for. I want to show you things. I want to compete with something that we do not know the answer. We do not know the entropy values for. So for that, we got the data from collaborators in the United States that are using the best supercomputer in the world in order to simulate protein fluctuation. And here we're using the protein this Wheeling headpiece folding. So it's a small protein that fluctuates between something which is more folded and something which is more free and random. And the way that they are doing that, and they are doing the simulation, again, it's a supercomputer simulation, all atoms simulation, very complicated. But the way that they can calculate the physical parameter of it, like binding and all of that things that interest, for example, Itai, is using that. So the enthalpy, the part of the internal energy, they know by the potentials of inside their simulations. However, in order to find the entropy, which I told you it's a big problem, what they do is they cheat. What do I mean by they cheat? They're using what is called transition-based method. What is transition-based method? They have a supercomputer, but then they go to the crystallographers and tell them, hey, can you just crystallize this protein and tell me how does it look when it's folded? And after I know how it is being folded, I can tell you when the frame in the simulation is in a folded state or in an unfolded state. And by the ratio of those time in the simulation that it's folded or unfolded, I can tell you a little bit about, I can tell you the thermodynamics of the problems. But this is cheating, right? Because if you have the crystal, why would you want to run a supercomputer? You can do all the experiments with that. We want to have the supercomputer to overcome all of our problems. So we can sit in our, backyard, run the simulations, and know the answer how to develop drugs. That's the idea. We don't want to use the experimentals, right? So what did we do? What we did is that we took the simulation data. The simulation data in each frame has the atoms' positions. We took the atom positions, and like with the string that I showed you before, we translated that to what is called Ramachandran angle. It's just the dihedral angles between the peptide bonds. And we use those values that appears there, organize them as a frame in a file. This file is this little string of numbers of the angles is part of a big data file. And we use compression algorithms. We found out how many frames that we actually need to take into account in order to get statistics about how much the system is folded when things are not moving around too much, and how much, and then we can see transition between one and another. And this is the big achievements that what we got in the end. So this graph is a bit complicated, but I'll tell you what we found. So what we have here is on the x-axis is the time of the simulation. It's a very long simulation. What is shaded in yellow is what is found according to the crystal structure as a folded state. The blue signal here are results coming from our simulation, from our analysis using compression algorithms, telling us what is the entropy state in each and every one of those frames. We have a value. It's not just folded or unfolded. It's not just binary 0 and 1. We have exact numbers in the right units, in the units of entropy, in the units of energy. And we can see that the correlation between those two estimates, one according to the experiments and one which I didn't use any of the experimental knowledge, is about 98 or 99%. And all done on a computer on the way to school, on a laptop on the way to school in the train. No supercomputer, nothing else. But this is not the biggest advances that we have. Because now we have numbers, not 0 and 1s, we can do something that was not be able to do before. We can actually construct a population diagrams of entropy and enthalpy. We can know exactly what states are more pronounced and what states are less pronounced. And we can see how that progresses with a different temperature, the simulation temperature that was done. How between a folded state and an unfolded state, how that is actually changing. And this is something that we could have never done before, using the same data that was available from the supercomputer. But last and not least, we can get another thing. What can we get? We have a bonus. And what is the bonus? The bonus is that we didn't use any of the crystal structure to do our analysis. We used zip. But we can find the low free energy state and know what exactly is the crystal structure of this protein without any prior knowledge, and then compare it to the crystal structure that is in the literature. So this is what we did. I spoke for a long time, rather fast. So if I need to summarize my talk, is about 3,000 words, I guess, or something like that. And to summarize it, take a log, as we just learned. And the log of that is about 3. So to summarize my talk, if you have a problem, just zip it. Thank you.
Thank you. Before I open the floor to questions, or a few questions, I have one. So you are confusing me, actually, because my limited capacity to understand, so entropy is defined by joules, by units of energy. What are the units of computational entropy?
So computational entropy is unitless, okay? It's just a probability, in a sense, it's without any units, it's just a probability to find a sequence, in a sense, later on in your string of text. So have the same meaning in that sense, but the units it's just without units in information theory. It's just missing the K-Boltzmann over there. So that's the answer, the short answer.
Yes, over there.
So I have 2 questions. So you have time series data.
Yeah.
Right? And you translate it to like a big file or like a big representation.
Yeah.
Over time.
Yeah.
So when you zip it, you have to choose like.
So we chose, yeah, so that's a good question. So what we did is that we actually chose the window that we have enough statistics so we can do the analysis, but it's not too big so we can actually see transitions. So we know that after about 2,000 frames or so, it's saturated in the amount of information that we are gaining. So we can just use that period of time and then just use a sliding window to get an estimate of the entropy at that period of time. And then we just do we take we just chop the files to smaller pieces, and then we estimate the entropy there, move it, estimate the entropy, and this is the line that you saw the estimation.
Okay. And in the example we showed, there were like 2 main states, like folded and unfolded.
But unfortunately, yeah, but it's not really that, right?
No, these are the extremes.
These are the extremes, yeah.
How can you differentiate between like different kinetic traps along the way, or like local minima versus global minima?
So we are doing that now with other collaborators. The thing is that people that are doing protein folding try to avoid all of those kind of things because it's really, really complicated in how to run the simulation for. But when we're using such a protein that do not fold into specific, we actually see the transition between places that are local traps that they can see, and then you will see like a minima in the entropy, but it wouldn't be a minima in the free energy because the enthalpy will still be high. So this is exactly the problems with simulation, that you need a balance of both entropy and enthalpy to know the true free energy minima. And this is the tools that we are providing now to learn about not just one, but both of them together, because they're not always go hand in hand together.
Okay, thank you, Roy. For the sake of time, let's thank Roy.